Welcome to the video lecture for section 13.1. This is for MGF 1106. My name is Hardik Aryan. So here we're going to be introduced to the basics of probability theory. We're going to learn how to calculate probabilities by counting outcomes in the sample space. We're going to use counting formulas to compute probabilities. We're going to perform computations using a relationship between probability and odd. And then finally, we're going to use probability theory to investigate genetic diseases. And so probability in everyday life, random phenomena are occurrences that vary from day to day and case to case. So we're not sure how it's going to turn out. Sorry about that. How it's going to turn out. But we can also often calculate a number that's called a probability. An experiment is any observation or random phenomenon. The different possible results of the experiment are called outcomes. Now, the set of all possible outcomes for an experiment is called a sample space. So we're going to determine a sample space for each experiment. We select an iPhone from a production line and determine whether it is defective. 3 children are born to a family, and we note the birth order with respect to gender. We select one card from a standard 52 card deck, and then without returning the card to the deck, we select a second card. We're going to make the assumption the order in which we select the cards is important. And then we roll 2 dice and observe the pair numbers showing on the top faces. So we select an iPhone from a production line and determine whether it is defective. The sample space is it's either defective or non-defective. Those are the only 2 possible outcomes. For 3 children that are born to a family, we can use a tree diagram to help find a sample space. And so this is the first birth, and then the second, and then the third birth. So we can have a boy or girl in the first one. Once we have a boy, the second child can be either boy or girl. If we have a girl, the second child can be either boy or girl. Once you have the first and the second child, the third child, if it's boy, it can either be a boy or a girl, or it can be a boy, girl, or boy, girl. And all of these final branches are all of the possible outcomes. So you can see that it goes all the way from boy, all the way down to girl. And the sample space includes all of these possible combinations. Oops, let me keep it. So this is the sample space, and this is the tree diagram that allows us to write that sample space. Now, we select one card from a standard 52 card deck, and then without returning the card to the deck, we select a second card. We're going to make the assumption that the order in which we select the cards is important. So the sample space is too large to list. However, we can use a fundamental counting principle from the previous section to count its members, because we can choose the first card in 52 ways. And the second card in 51 ways. Since we're not replacing the first card, then we can select 2 cards in 52 times 51, which is 2,652 ways. Now we roll 2 dice and observe the pair numbers showing on the top faces. So this is a sample space for 2 dice, and I've already shown you this previously. So there's 36 possible pairs, or 36 possible outcomes. Now, in probability theory, an event is simply a subset of the sample space. So we're going to write each event as a subset of the sample space. A head occurs when we flip a single coin. 2 girls and 1 boy are born to a family. A total of 5 occurs when we roll a pair of dice. And so the first one, the set just ahead, is the event. So 2 girls and 1 boy are born to a family. Now, noting that the boy can be first, second, or third, the event will be boy, girl, boy, girl, or girl, boy. And we can get that from the previous sample space that we found. Then a total of 5 occurs when we roll a pair of dice. And so the following set shows how we can roll a total of 5 on 2 dice. Now, the probability of an outcome in a sample space is a number between 0 and 1 inclusive. The sum of the probabilities of all the outcomes in the sample space must be equal to 1. The probability of an event, E, is written as P of E, is defined as the sum of the probabilities of the outcomes that make up E. So, empirical assignments of probability. If E is an event and we perform an experiment, If E is an event and we perform an experiment several times, then we can estimate the probability of E as follows. The probability of E is equal to the number of times E occurs divided by the number of times the experiment is performed. So this ratio is sometimes called the relative frequency of E. So here's an example. A pharmaceutical company is testing a new flu vaccine. The experiment is to inject a patient with the vaccine and observe the occurrence of side effects. Assume that we perform this experiment 100 times and obtain the information in the following table. Now, based on the table, if a physician injects a patient with this vaccine, what is the probability that the patient would develop severe side effects? So here, number of times, right? None, 72, mild, 25, and severe side effects is 3. So we're looking for the severe effects, and so if we can see here the number of times that E occurs over the total number of experiments that's performed, we get that is 3 over 100, or about 3%. Now, this following table summarizes the marital status of men and women in the United States between the ages of 18 and 34 in a recent year. All numbers represent thousands. If we randomly pick the male, what is the probability that he is married but not separated? So here's the table. Here's the males. 9,740 males are married and not separated. 36 are widowed, 1,621 divorced or separated, and then 24,655 are never married. Females, 12,279 now married and not separated. Widowed, 104, divorced or separated, 2,328, and never married, 20,449. So we're only interested in males, so we consider a sample space to be a total of 36,052 males. The event, we call it M, is a set of 9,740,000 males who are married but not separated. So then the probability of the number of males divided by the total sample space for this particular cell right here is going to be 0.27. Now, probabilities. They may be based on empirical information, for example, the result of experimental data, or probabilities may be based on theoretical information, namely combination formulas. So if we flip 3 fair coins, what is the probability of each outcome in this sample space? So each equally likely outcomes are shown below. Each has a probability of 1/8. So you can see we flip 3 coins. We can go all the way from H, H, H to T, T, T. And this is the same sample space for the 3 children. Now, how do we calculate probabilities when outcomes are equally likely? If E is an event in a sample space, S, with all equally likely outcomes, and the probability of E is given by the formula, the number of E divided by the number of S, or N of E divided by N of S. So what is the probability in a family with 3 children that 2 of the children are girls? So we saw earlier that there are 8 outcomes in the sample space. We need to denote the event that two of the children are girls by the set G, capital G, and this is the outcomes for that particular outcome that we're looking at, the sample space. So it's going to be 3 over 8. Now, what is the probability that a total of 4 shows when we roll 2 fair dice? So the sample space for rolling 2 dice is a set of 36 ordered pairs. And so the roll of total of 4, there's 3 possibilities. So it's going to be 4 over 36, or 1 out of 12. If we draw a 5-card hand from the standard 52-card deck, what is the probability that all 5 cards are hearts? And so here we're going to use combinations. So there are 52 choose 5 ways to select a 5-card hand from the 52-card deck. If we want to draw only hearts, then we're selecting 5 hearts from the 13 available, which can be done in combination of 13 choose 5 ways. There's a probability that all 5 cards selected will be hearts. It's simply 1,287 over 2,598,960, which is 0.000495. So what are some basic properties of probability? Assume that S is the sample space for some experiment E. So then the probability of E is between 0 and 1 inclusive. The probability of E not occurring is 0, and the probability that the event is going to occur is 1. So everything is between 0 and 1. 0 means it's not happening. If it's certain, it's a probability of 1. Now, if the outcomes of a sample space are equally likely, then the odds against an event E are simply the number of outcomes that are against E compared with the number of outcomes in favor of E occurring. Now, we can write these odds as the complement of E to the event of E, if you will, where E complement is simply just the complement of E. So if you have 2 outcomes, let's say heads or tails, then tails would be the complement of heads. And so if a family has 3 children, what are the odds against all 3 children being of the same gender? So you can see that there's 6 against, and then 2 in favor of them being the same gender. And so it's 6 to 2, or 1 to 3. So the odds are 1 to 3. Now, a common type of roulette wheel has 38 equal-sized compartments. 36 of the compartments are numbered 1 through 36, with half of them colored red and the other half black. The remaining 2 compartments are green and are numbered 0 and 0, 0. Small ball is placed on the spinning wheel, and when the wheel stops, the ball rests in one of the compartments. What are the odds against the ball landing on red? So this is an experiment with 38 equally likely outcomes. Because 18 of these are in favor of the event, the ball lands on red, and 20 are against. The odds against red are 20 to 18. Now we can write this as 20 to 18, which we can reduce to 10 to 9. Now, if E prime is the complement of the event E, then the odds against E is simply the probability of the complement of E divided by the probability of E. So what are the odds against surviving an airplane crash? The safest place to be seated in the event of an airplane crash is in an aisle seat above the wings. In this case, the probability of surviving a crash is 56%. So what are the odds against you surviving? So the probability against, L, is 0.44. The probability in favor is 0.56. So therefore, it's going to be 0.44 over 0.56, which turns out to be 11 out of 14. Now, here capital Y produces yellow seeds, dominant gene. Lowercase g produces green seeds. This is a recessive gene. So parent 1 and parent 2. So parent 1 is a YY, parent 2 is a GG. So each offspring will have one Y gene from parent 1 and one G gene from parent 2. And each will have yellow seeds. That's the first generation. Now, crossing 2 first-generation plants. Each offspring will have either a Y gene or a G gene from each parent. So only the seeds of the offspring with the GG pairs of genes will be green. So you can see that you can have a YY, YG, GY, or GG. So first generation plant, you have YY, YG, GY, or GG. That's a recessive gene. And then, so this leads to this next question. Sickle cell anemia is a serious inherited disease that is about 30 times more likely to occur in African American babies than in non-African American babies. A person with 2 sickle cell genes will have the disease, but a person with only 1 sickle cell gene will be a carrier of the disease. If 2 parents who are carriers of the sickle cell anemia have a child, what is the probability that each of the following? The child has sickle cell anemia, the child is a carrier, and the child is disease-free. Now, the table in the next slide shows the genetic possibilities when 2 people who are carriers of the sickle cell anemia have a child. We're going to denote the sickle cell gene by S and the normal gene by N. Now, we use lowercase letters to indicate that neither S or N is dominant. So as you can see, we have SS, SN, NS, and NN. So the child has sickle cell anemia is 1/4. The child is a carrier is 1/2, and the child is disease-free is 1/4. And that's the end of section 13.1. Thank you.